Hello and welcome to this GCSE Chemistry explanation video about mixtures. In this video, we'll start by looking at what pure substances are and compare them to mixtures, and then we'll focus in on the different separating techniques that you need to know about. We'll look at filtration, crystallization, chromatography, and distillation. All substances in the world are made out of atoms. This doesn't matter whether we're talking about gases or solids or liquids. All of these substances are made out of atoms. And an atom is taken to be the smallest amount of a substance that you can have whilst it still remains that substance. And we can show atoms in particle diagrams, and they're typically represented by circles, and different atoms have got different colours. Elements are substances that are made from only one type of atom. And these diagrams show examples of different elements with their particles arranged in different ways. But what they have in common is all of the particles and all of the atoms in any of these boxes are the same size as each other and they're shown as being the same colour as each other. So there is only one type of circle, one type of atom in each of these boxes. That doesn't matter whether we've got separate atoms, many atoms joined together, or if the atoms are in pairs. They are all only made up of one type of atom. And so an atom is taken to be the smallest part of an element that can exist. Compounds are substances that contain two or more different elements that have been chemically combined. We sometimes refer to it as being bonded together. And you can see that from these diagrams here. I'm showing a variety of different compounds, and each of the compounds has got more than one different coloured atom being shown in its diagram. And that's how we know it's not a pure element anymore, because we've got different coloured circles representing those different elements that have been chemically combined. The bonds that hold atoms together in a compound are very strong, and that's something that influences the properties that different compounds can have. Another feature of this is that compounds can only be separated out into their component elements by chemical reactions. And so that means that we can't use physical methods of separation that we can do for some things that have been mixed together. We have to use actual chemical reactions to pull apart the elements and to break the bonds that have been holding them together. Pure substances are taken to be substances which are only made of one type of particle. And it doesn't matter whether this is an element or whether it's a compound. We can have it as being pure if all of the particles are the same. And so in my top example, we've got these atoms that are separated, and this is an element, and all of these particles are the same. And we've got another element at the bottom left, but what we can see is that all of the particles in this box are the same. And so this is a pure element. And we've got another pure element in the top middle. All of the circles are the same colour, all of the particles are the same, and so these are 100% pure because there is only one type of substance. The remaining three examples are compounds, but in each example, all of the compounds are identical. This one at the bottom has got two of the atoms that are shown as being black and one atom shown as being red, but every single one of these compounds are the same. And this one bottom right, all of these compounds have got one black circle and four orange circles, and so that's all the same compound. And on the top right, this compound is pure as well because all of the particles have got one blue atom and one orange atom, and so the compounds are always the same because they're always in the same ratio in each of the examples. So 100% pure, all of the particles are the same. Mixtures are different to elements and compounds because they aren't pure. A mixture consists of two or more elements or compounds that are not chemically combined together. And we can show that in particle diagrams. We've got different types of particles that are in the same place and they're shown as not being touching, and that is symbolizing the fact that they are not chemically combined. They aren't bonded together. And you can have mixtures of all sorts of different substances. In the left-hand diagram, we've got a mixture of two different elements in the same place but not chemically combined. In the second example, we've got two different compounds that aren't bonded together, they're just mixed together. And then in the third diagram, we've got an element and a compound mixed in the same place. In compounds, the elements always combine in fixed proportions or in a fixed ratio. And you can see that for my middle example where I've got one blue atom and one red atom in every single example of this compound. Unlike compounds, mixtures can be formed in any ratio at all. And you can see that in these three examples at the bottom of the screen. They are all mixtures, and they are all mixtures of the same substances, but each of the mixtures contains the substances in a different ratio, and that's totally possible for mixtures. Any ratio at all is still classed as a mixture. Since the components of a mixture aren't chemically combined together, the substances in the mixture retain their properties, and the mixture themselves have properties which is a combination of the properties of the components in the mixture. And so the chemical properties of each substance in the mixture are unchanged. And we can separate the substances out from a mixture, provided that the two substances or three substances in the mixture have different properties. Examples of properties that we can use to separate substances out from a mixture are whether or not these substances are magnetic. And an example of this would be if we had sand mixed in with some tiny pieces of iron, some iron filings, we could use a magnet and bring that magnet close to the mixture, and the iron is magnetic, and so that would be separated out from the sand because the sand is not magnetic. We can also use particle sizes. We also might have mixtures where the components might have different solubilities, or where we've got mixtures that have got different boiling points. That's normally used where we've got different liquids that are mixed together. You need to be aware of 5 different separation techniques. You need to be able to explain how they work and suggest examples of mixtures that you might separate using that technique. And these techniques are filtration, crystallization, simple distillation, fractional distillation, and chromatography. And each of those techniques uses a physical process to separate the mixture, and they don't involve any chemical reactions at all. And the diagram at the bottom of the page illustrates the physical separation technique. We've got the mixture on the left-hand side, 2 different elements, the blue molecule and the green atoms, and we carry out some kind of separation technique, and we end up with separated green atoms, and the blue molecules are also separated as well. And we can tell that we have used a physical process to separate the mixture, not a chemical reaction, because these substances were present at the beginning and they're present at the end. So no new substances have been made. And these substances that we've separated out behave in the same way as other examples of those substances that have never been mixed together at all. They've got the same properties of all other substances of that type. Filtration is a separation technique that uses the property of particle size to separate the components of the mixture. We would use this to separate an insoluble solid from a liquid. An example of a mixture that you could separate this way is sand and water. To separate this mixture, you would need to get a filter funnel and a filter paper, which you'd fold into a cone shape and put the paper inside the funnel. And then you would sit the funnel into a conical flask and pour that mixture through the funnel. And what would happen is the insoluble sand would get caught on the filter paper and the rest of the water would move through into the conical flask, and we've separated our mixture. This works because the sand particles are much larger than the water molecules, and filter paper actually has a series of holes or pores in the paper itself. And the water molecules are small enough to pass through these holes, but the particles of the sand are much too big, and so they get trapped on the top of the paper and are unable to pass through. And so the filtration technique removes solids. This would work in the same way if there was something dissolved in the water. Anything dissolved in water has been broken up into such small pieces, far smaller than we can see, and these pieces are also small enough to pass through the filter paper. And so dissolved solids can also pass through filter paper and can't therefore be separated in this way. And so filtration is only used when we want to separate an insoluble solid from a liquid. Crystallisation is a technique that we use to separate soluble solids that are dissolved in a solution. Common examples of where we might use this technique are to separate sodium chloride or table salt out from salt water, or to separate copper sulfate out from a solution. To carry out this technique, we need to transfer our solution into an evaporating basin. And then typically the evaporating basin is placed on top of a beaker, which is placed on a tripod with a Bunsen burner underneath. And then we'll use this Bunsen burner to warm up water in the beaker underneath the evaporating basin. And then once that water is turning into steam, that will transfer the heat energy to the solution that's in the evaporating basin. And that liquid will start to evaporate from the solution, and the volume of solution in the evaporating basin will decrease. Once some of the solvent has evaporated from the solution, we would turn off the heat from this Bunsen burner and we would allow the evaporating basin to cool down to room temperature. The solvent, that's the liquid that the solid was dissolved in, will continue to evaporate, but it will evaporate much more slowly now. And so it might take a matter of days for this evaporation to take place. It will take place faster if you put your evaporating basin somewhere warm or on a window ledge in direct sunlight. We can also dry the solution in some kind of drying oven, so that's an oven that's not too hot, or a desiccator. Either of those, the solvent will gradually evaporate from the solution and we'll be left with crystals of our copper sulfate, for instance. Instead of carrying out the technique like this, we can sometimes heat the solution directly with a Bunsen burner. And this is a much faster technique, as you can probably imagine. But we don't always prefer to use this method for a number of reasons. First of all, if the solvent is highly flammable, this technique is much more dangerous. It's far better to not heat the solution directly. And in that case, we might actually choose to heat it with some kind of hot plate instead of any kind of Bunsen burner at all. Additionally, the crystals that form from the more direct evaporation of all of the solvent are much smaller than those that you get from the more gradual crystallization, where you've reduced the volume and let it evaporate the rest of the way naturally. And we get much larger crystals that way. Not only that, some crystals are more temperature sensitive than you might imagine, and if we heat them directly using a Bunsen burner pointed straight at the evaporating basin, sometimes those crystals can decompose and fall apart and change into something that we don't want to happen. And that's why the preferred method is using this water bath technique and letting the rest of the solvent evaporate naturally in a warm place. Chromatography is a separation technique that uses the property of solubility to separate the different components in a mixture. Typically, we'll use this to separate different coloured dyes from something like an ink. In this technique, what we do is we take a piece of chromatography paper or filter paper, and we mark a pencil line on this paper, and on this line we place our sample that we're going to separate. And this sample will be a mixture of different colours that was all together in the same place at first. And then we place our piece of paper into a beaker that contains a solvent. Typically, this solvent might be water. It's very important that the line where we place our spots has been drawn in pencil, because if it wasn't drawn in pencil and was drawn in pen, when that solvent reaches the ink, which it will do over time, the line will dissolve as well, and that will interfere with our experiment, and it will rise up the paper and blur in with our spots that we're hoping to produce. Because the solvent might not be water, it might be something like ethanol, which evaporates quite easily. We sometimes put a lid on our chromatography experiment because that will reduce the rate at which the solvent evaporates. It's really important to make sure that the level of the solvent touches the paper but doesn't go above our starting pencil line. If it does, the spot will dissolve in the solvent and the water will take up the colour of that solvent, rather than what we want to happen, which is that the water rises up the paper, and when it reaches the pencil line, the ink that is on the paper will dissolve in the solvent and gradually rise up the paper as the water rises up the paper. What we will see happening is the different dyes that make up the ink will travel up the paper at different rates. And so eventually those inks will separate out and form spots. And these spots will travel up the paper and finish in different places. We will stop the chromatography when the solvent has got towards the top of the paper. It doesn't need to get right to the top, but towards the top, because that will allow the greatest separation for our spots. Once the solvent has risen towards the top of the paper, it doesn't need to be the very top, we take the paper out of the beaker and we mark on how far that solvent has got. This is referred to as the solvent front. And then we will draw around the spots in a pencil and mark on how far those spots have travelled as well. We will always make our measurements from the starting line, sometimes referred to as the baseline, that we drew in pencil, and we measure from that line to the solvent front, or from that line to the spot. And we always measure our spots from the middle of the spot because they're unlikely to be perfectly circular. This completed picture that we get from the pattern of the spots on our paper is called a chromatogram. And we can use a chromatogram in a variety of different ways. First of all, we can determine whether or not a sample is pure, because if it is pure, we will only get one spot on our paper. We can also look to see how many components there are in a mixture. And the number of spots that we see having separated out tells us the number of inks that there were in the original sample. If we see 3 spots on our chromatogram, there were 3 inks in the original sample. If there are only 2 spots, then there were only 2 inks in the original sample. Another way that we can use our chromatogram is by comparing the substances contained in the different samples. For instance, we can see that for our substance X and substance Y, they didn't have the same number of substances, but their red coloured dye appeared to travel the same distance up the paper, and that suggests that they are the same dye. And in the same way, the light blue coloured dye in X travelled the same distance as the light blue dye in Y, and that suggests that they are the same dye as well. And substance Z, whilst it had a red coloured dye, it must have been a different red dye to the dye in X and Y, because otherwise it would have travelled the same distance, and there isn't a red spot in this position. The red spot for Z did not travel to such a height that they did for X and Y, which suggests it's a different dye. And we can also compare our samples that we've tested to a set of reference values. Perhaps we could have some reference values for a range of different coloured red dyes, and we could identify that the red dye present in Z is this one because this known sample of red coloured dye travelled the same height that Z did. And the red colour in X and Y travelled the same height as this colour, and so that means it is this red dye. And there wasn't any red coloured dye that travelled any higher than that, so those other known dyes that were red weren't present in either of our three samples. The final way that we can use our chromatogram is by making statements about the solubility of the different substances. The further a dye has travelled, the more soluble it is in the solvent that we used. And so this dark coloured dye, this blue dye that's present in X, appears to be the most soluble of all of the substances tested because it travelled the furthest up the paper. And that's a characteristic of a more soluble dye. And then the red colour in Z travelled the least distance up the paper, and that means it is the least soluble of all the dyes that were tested. Simple distillation is a technique that we use to separate mixtures that contain at least one liquid. And the property that we're taking advantage of to separate our liquid out from the mixture is its boiling point. If we were using a mixture of two liquids, we could use simple distillation if those two liquids had different boiling points. Or we could use this technique to separate a mixture of a liquid that has got some kind of solid dissolved in it, for instance with seawater. The process of distillation can be used to remove the salt from seawater and to produce drinkable water as a result. This involves firstly heating the water in a flask or in a tank, depending on the scale that you're carrying this out on. And when this happens, the water will boil and steam will form. And then this steam will rise up and out of the flask, leaving behind any dissolved salts as a solid in the flask. And then the steam will move through the distillation apparatus and it will condense back into water as it cools down. And the liquid water will usually form in the condenser and it will dribble down into the collecting vessel at the other end of the apparatus. If we'd been separating a mixture of two different liquids instead of separating the water out from salt water, the liquid that has the higher boiling point would be the one that stays behind in this flask, because the one with the lower boiling point boils more easily and therefore would evaporate first and then travel through the apparatus and condense in the condenser and then collect in the collection vessel, this conical flask on the right-hand side. Fractional distillation is very similar to simple distillation in that the mixture that we are separating is of liquids, and these liquids have got different boiling points. The apparatus differs slightly, and the main difference is that we have an additional piece of glassware called a fractionating column just above the flask where we've heated our liquid. The purpose of this fractionating column is to slow down the movement of the vapours that have been produced in this flask. So the liquids will have different boiling points. The liquid with the lowest boiling point will evaporate first and rise up from the flask into the fractionating column, and then it will move across into the condenser, turn into a liquid, and then drip into the collection flask over on the right. If the liquids in the original mixture have got quite similar boiling points, this can cause problems if you're using simple distillation, because what can happen is more than one of the components in the mixture can evaporate at the same time, and you can end up collecting a mixture in your collection flask. And this is where the fractionating column becomes really important, because the liquid with the lowest boiling point will evaporate first and start to rise up into the column. But then not long afterwards, the liquid with the next lowest boiling point will evaporate, and that will rise up into the column as well. And because the fractionating column is such a large piece of glassware, it ends up being hotter at the bottom and colder at the top. And because the vapours are moving through this quite slowly because of the glass beads that are inside the column, it gives the vapours more chance to cool down and condense and run back into the original flask. And that's why the liquid with the lowest boiling point is able to evaporate and move around the corner more quickly than the one with the higher boiling point, because the higher boiling point vapour gets 2/3, a third of the way up, and then it condenses and moves back into the flask. And this means that we're able to separate liquids that have got similar boiling points. And we can track this quite carefully using the thermometer that's at the top of the column. When the first liquid has been collected, you will notice a change in the thermometer when the next vapours start to move past. And so what that means is you can swap out this first conical flask and you can collect the next liquid in a new container. And when the reading on the thermometer changes again, you can swap it out again and again until all of the components in the mixture have collected in their own conical flask. And so we've been able to separate 3 or 4 different liquids, and we've done it even though these liquids might have really similar boiling points. And this technique is useful in all sorts of industries, particularly in crude oil, separating the different parts of crude oil into different fractions.